Welcome back, everybody. This is our fifth class in NEET previous year questions for chapter Moving Charges and Magnetism of class 12th. Before this, in this series for this chapter, we have made 4 videos, and all of those videos are available on our YouTube channel. We have also started similar series for JEE previous years, and videos regarding to that playlist are also available on our channel. If some of your friends are preparing for JEE, or if you want to have a look on or taste of some harder questions, then you can try those out. So again, and if you find these videos useful, then do press the like button, share them as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. With this, let's start today's video. In the previous one, we were around 40. This was the last question, and today we will start move further. So, if a long, hollow copper pipe uh, carries a current, then magnetic field produced by inside it, outside, both inside and outside, and nowhere. So, suppose we have a pipe of something like this. Now, if inside of this pipe, as it is hollow, and if I make a Amperian loop here and write equation for that B dot dl is equal to mu node I. As it is a hollow pipe, so from this part there is no current. So this term reduces to zero, or we can say magnetic field is zero. Now, if I make a bigger Amperian loop, such that it is outside of the hollow pipe, then what would it mean? That it will encompass this hollow cylinder, and hollow cylinder has some current, means in that scenario there will be non-zero value of mu node I. So outside we will get a magnetic field, but inside magnetic field will be zero. So magnetic field will produce only outside. Let's move to next one. A coil of one turn is made of a wire of certain length, and then form of same length a coil of 2 turns is made. If the same current is passed in the both of the cases, then the ratio of magnitude of magnetic induction at the centers. We have solved this type of question already in the previous videos, and where uh, we have come to the conclusion that we have a loop and we have a coil with n turns. So, provided condition that current is same, and second, total length is same, then we can write that if this coil has n number of turns, then magnetic field at the center of the coil is n square times the magnetic field at the center of loop. So first here we have a coil, and then we have a loop, and we have to find their ratio of their magnetic fields. So we can say B coil by B of loop will be n square, and n is equal to is a number of turns. Here we have 2 turns, so 2 square is 4, so it will be 4:1. That is option C for us. Let's move to the next question. Two equal electric current are flowing perpendicular to each other as shown in the figure. AB and CD perpendicular to each other and symmetrically placed with respect to the currents. Where do we expect the resultant magnetic field to be zero? So here this whole diagram is a 2D diagram. First of all, that needs to be understood. Understood? And here we have conductor. Suppose this is x direction, this is x and this is y, and out of the paper there will be z direction, and let me draw z also. So suppose this represents a z direction. So now let's find out direction of magnetic fields. Now for wire, we can say for this horizontal conductor, magnetic field, if we apply right hand screw rule, then magnetic field will be going behind the conductor, and coming like this. So if we discuss in the first coordinate here, magnetic field due to this conductor, horizontal conductor, will be outside or in the positive z direction. Now for this vertical conductor, if we apply right hand screw rule and your thumb points to y direction or in the upward, then you will find that magnetic field due to this will be going like this, means going downward. So here magnetic field will be going downward. So due to horizontal conductor, magnetic field is coming upward, and due to vertical conductor, magnetic field is going downward. So there can be a place if both of these current conductors are identical at same distance. Let me show you how. Suppose we consider a point here, and it is at distance d from conductor, horizontal conductor, and it is also distance d from the vertical conductor. So at this point, value of magnetic field due to horizontal and vertical conductor will be same but in opposite direction. So net magnetic field at this point will be 0, and as we know that d can take any value from 0 to infinite, so we will get a straight line something like this, at which value of magnetic field will be 0. So on AB line, we are sure that value of magnetic field will be 0. Now coming to the second quadrant here. Here, magnetic field due to horizontal conductor will be coming up, coming outward, and due to vertical conductor, it's also coming upward. So on this line CD, magnetic field will be added. So it will be twice. So on line CD, magnetic field will be twice, and on line AB, magnetic field will get cancelled. So we have been asked that where will be the resultant field to 0. So on line AB, resultant field will be 0. Moving to the next one. A straight wire of diameter 0.5 meter carrying a current of 1 ampere replaced by another wire of 1 mm diameter carrying same current. Strength of the magnetic field far away. So we have been asked that strength of magnetic field far away. And here we have to understand that initially we had a wire. Suppose this is our initial wire with 0.5 mm radius or diameter, and we have done another wire with 1 mm diameter, and we have to find a value of magnetic field at a far away point. So suppose point is here. Now we know that value of a far away point depends upon the value of magnetic field at this point depends upon this distance, the angles which it makes phi 1, phi 2, and the current in the wire, but does not depend upon the radius of the wire. So whatever will be the radius of the wire, if these variables, distance, value of current, and value of phi 1, phi 2 remains constant, and another condition also that this distance d is very large as compared to the radius, then magnetic field will stay constant or will stay the same. So same as the earlier value. Moving to the next one. A long solenoid of radius 1 mm has 100 tons per millimeter. So value of n, that number of tons, is 100 per millimeter, means divided by 10 raised to power minus 3. So it will be 10 raised to power 5. Value of current is given, magnetic field at the center we have to find. So magnetic field at the center of a solenoid is mu node n times I. So it is 4 pi into 10 raised to power minus 7 into n 10 raised to power 5 into current, that is 1. So 4 pi into 10 raised to power minus 2, and 4 pi is 12.56 into 10 raised to power minus 2. That is option B for us. Moving to the next one. Long solenoid of 50 centimeter length having 100 tons carries current 2.5 ampere. Magnetic field at the center we have to find out. So here length is given and 100 tons it has in a 50 centimeter length. So that n in the formula B is equal to mu node Ni. It is number of tons per unit meter, and we have 100 tons in 50 centimeter. So per unit per meter it will be 200 tons. So putting value 4 pi into 10 raised to power minus 7, n is 200 and I is 2.5. 2.5 into 4 is 10, and that 10 will be adjusted here. So 10 raised to power minus 6 minus 4 and 2 into pi, that is 6.28. So option D will be the right answer here. Moving to next one. A long solenoid of diameter 0.01 has a tons per meter. So we know the radius, we know the number of tons. The center of solenoid, a coils of 100 tons of radius, and this value placed with axis coinciding with the solenoid axis. The current in solenoid reduces at the rate from 0 to 4, 0 ampere from 4 ampere in 0.05 second. If the resistance of the coil is this, total charge flowing through the coil during this time. So we have to find total charge. What we can do? First of all, we need to find the amount of magnetic field. So let us write out all the variables. So we have a diameter of solenoid, that is 0.1. So radius of solenoid, that is zero point 0.1 by 2, and n for solenoid, that number of tons, that is 2 into 10 raised to power 4. And at the center of solenoid we have a coil. So for radius of coil is 0.01, and number of tons for coil and C are 100. Now it is mentioned that current changes. So what we will do here, we will apply the formula for the induced EMF, because we have to find the amount of charge, and charge can be found out by multiplying the to current to time, then we can get the charge. So starting with the basic formula, that EMF induced is given by d phi by dt, and we know from the formula of mutual inductance that d phi by dt is also is equal to m di by dt. Here E is the induced EMF. Now from the induced EMF, if we know the resistance which is given to us, resistance of the coil RC is 10 pi square. We know from the Ohm's law that V is equal to IR, and this is the potential, so it will be I into R is equal to M di by dt. Now there is difference between this I and this I. This is rate of change of current and this is actual I. Now we can write current, as we know that current is dq by dt. So we can write it q times t. So it will be q that is the charge, into resistance by time is equal to m di by dt, and from here amount of charge will be time by resistance into m into di by dt. Now we know the value of mutual inductance, that is mu node n1 n2. If we have we can say two solenoid or two coils, then one of them is referred as first and then second is referred as second, into area divided by this r. This is the value of m. We have resistance here and we have time and di by dt here. So let's substitute all the values. So mu node is 4 pi into 10 raised to power minus 7. N1 we have 2 into 10 raised to power 4. N2 we have 100. And here these N1 and N2s are the actual values of number of tons. These are not number of tons per unit meter. For that, if we take number of tons per unit meter, then that formula is different slightly. Here, as we don't know the length, so we are using the formula which has actual values of the number of tons. And here, area is the area of the coil. So pi, radius of coil is 0.01 or 1 into 10 raised to power minus 2, squaring that 10 raised to power minus 4 divided by the resistance, that is 10 pi square, multiply by time, that is 4, and di by dt, that is change in current is 4 with in time. Oh, sorry. Here value of time is 5 into 10 raised to power minus 2. And here we have time 5 into 10 raised to power minus 2. So this value get cancelled, pi square get cancelled, and we are left with 4 into 2, 8 into 4, that is 32, multiply minus 7 plus 4, minus 3, minus 3, minus 4, minus 7, and here we will get one more, I think. So minus 8 multiply 100 we have, so 10 raised to power minus 6. Here this plus 4 minus 4 get cancelled. We have 100 here, so 10 raised to power minus 5 divided by 10, so 10 raised to power minus 6. So 32 microcoulomb, that is the answer for this question. Moving to the next one. An arrangement of three parallel straight wire placed perpendicular to the plane of paper carrying same current I along the same direction as shown in the figure. Magnitude of force per unit length on the middle wire is given by. So on the middle wire we have to find magnitude of current, and these are parallel, same current I in the same direction. So they are carrying the current in the same direction. So for that, what we can do, as let's start with conductor C. We have to find magnitude of field or magnitude of force on the conductor P. Again, direction of the current is same in every. So as direction of the current is same, so they will attract each other. So assuming that C and A are stationary, so force on B due to C as the same direction, it will be towards C, and A and B also have same direction, so force on B from A will be again towards A. So forces will be at right angle, and magnitude of forces per unit length, that is given by mu node I by twice pi d into current of second conductor, and as current is same, so it will be mu naught I or mu naught I square by 2 pi t. So this is the force per unit length in the positive x, and this is the force per unit length in the negative y. So vector form of force or total force will be mu naught I square 2 pi t of I negative mu naught I square 2 pi t of minus j. And if we find out the magnitude, so ft magnitude will be mu naught I square 2 pi d, here I square plus j square, that will be root 2. So option D will be the right answer here. Let's move to the next question. Square loop ABCD carrying current I is placed near and coplanar with the straight conductor XY. So there is straight conductor XY carrying a current I. The net force on the loop will be. So we have to find out the net force on the loop. And as per direction of the current, we have current here, 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 and here. So let's first figure out the direction of the magnetic field. Now due to this conductor I, it will produce the magnetic field such that, using right hand screw rule, that magnetic field will be going into the page on the right hand side. So on the right hand side magnetic field, we can say B is in B node with negative sign of K. So now let's first find magnetic field or the force on conductor AB. Assuming this conductor XY is infinite conductor, so it will produce a value of magnetic field. Our formula for magnetic field for infinite conductor is given by mu naught I by 2 pi t. So force on AB will be given by I, that is the current in the conductor AB. So let's write it small I into L cross B. Here direction of length will be according to direction of the current, means in the positive x direction. So it will come out to be, so this is I only, not I vector. So length is L I. This is I for current. Let me use it I2 so that there is no problem or no mistake. Thus current is I2. And this I is unit vector. Cross product with the magnetic field at AB, magnetic field will be mu naught I 2 pi d with minus k sign. So force will be mu naught I2 of I into L by 2 pi, distance that is L by 2, distance from the conductor, that is L by 2, into I cross minus k. Now I cross minus k can be written as k cross I, and k cross I is j unit vector, means force will be in the upward direction, and it can be written as mu naught I2 I L divided by pi L into j. Now let's come to the second conductor CD. So force on CD, here current is same I2, length is same L, but direction is reverse of current, so it will have minus I cross value of magnetic field mu naught I by 2 pi, and distance is also changed, L plus L by 2, that is 3L by 2. So 3L by 2 into direction of the field is same minus K. So we will have here mu naught I2 IL by 3 pi L into minus I cross minus K, or we can say I cross K, that is minus J. So force on AB conductor is in the upward direction and force on the CD conductor is in the downward direction. Sorry for the mistake, we made a mistake. That length is in Y direction. I took in the I direction. Here length is along Y axis, so it will be J. And if it is J, so we have J cross here, J cross K with minus sign, so it will be minus I, so it will be minus I, and it will be minus J, so it will be plus of I. So that's the mistake I made, as in this case length of the conductor is in the downward direction and downward direction is minus Y, not the plus minus I. I got confused with this X. That's why that mistake happened. So for AB and CD, we calculated the amount of forces. For AB, force is in minus I, so it is attracting attracted towards the conductor, and CD is getting repelled from the conductor, which we can guess from the basic that when we have current in the parallel direction, they attract, and when they have opposite, then they repel each other. Now coming to the BC and CD. Now for BC and CD, we will not directly calculate. Why? Because the forces will cancel each other. Now first of all, it's difficult to calculate. Why? Because here, as we move from B to C, then the value of magnetic field is changing, because value of magnetic field due to this conductor depends upon the distance of this conductor from the place where we calculate the magnetic field. For conductor AB, the distance is same. For conductor CD, the distance is again constant. But for the BC, the distance is variable. So what we assume? We assume that we take a average value of magnetic field. Suppose that is B, and that is same for both BC and AD, as average distance for both of these is same. And now if we calculate the value of force on BC, that will be I. Its length is L, and in length is in positive X direction, so L of I. And suppose value of magnetic field is B. We are just assuming it to be node. Suppose average value, certain average, and direction of the magnetic field is in the negative K direction, so minus of K. And this will give us I L B node, I cross K, that is minus J, or plus J, that is the total value. Now similarly for the AD, if we find out, it will be I. Here length will have opposite direction, so L of minus I cross magnetic field will stay the same, because we are taking average value, and this will give us I L B node with minus J sum. So forces for these two conductors are equal and opposite, so they will cancel out each other. But forces for AB and CD are opposite in direction but not equal in magnitude, so they will not cancel each other, and net value will be their subtraction. So net force will be, we can say, their vector sum, as they have the same direction. If I forgot to make it I, so mu node I2 I L by pi L plus mu node I2 I L by 3 pi L. That will be the net force. And if we can take common, mu node I2 I L by pi L is common, so minus 1 plus 1 by 3, that will be minus 2 by 3. So minus 2 by 3 mu node I2 I L by pi L means the force will be attractive, and L get can cancel, so I by pi mu naught I by pi into 2 by 3. So option D will be the right answer here. So with this, we end this video here. Again, if you find this video helpful, useful, then do press the like button, share it as much as possible and subscribe to our channel. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching and we will meet in next video.